Oh, heat. We have confirmed for the first time the death of a star at the edge of the observable universe. This isn't a simulation or an artist's rendering. It's real light, a fossil from an explosion that occurred when the cosmos was a tiny fraction of its current age. And what this ancient death reveals about our own cosmic history is frankly remarkable. But last year earlier, we finally captured a supernova as it was exploding, and on purpose, finding it just hours after it began. This is one of the earliest detections we've ever made, and it's shown us something we've never seen before. The shape of the explosion. It might sound like an unusual thing to get excited about, but this discovery has the power to unlock the inner workings of exploding stars and answer centuries-old conundrums. What are the mysterious mechanisms that drive a supernova? How does a core collapse inward, then suddenly explode outward? Thanks to new data on an object named SN 2024 GGI, we're inching closer to answers. On the night of April 10th, 2024, an automated survey called Atlas was conducting a routine sweep of the cosmos. Atlas isn't just looking for asteroids that might threaten Earth. Its constant scanning of the night sky makes an incredible tool for spotting transients, things that suddenly appear or change in brightness. And on this day, that's exactly what happened. In the spiral galaxy NGC 3621, a beautiful island of stars about 22 million light-years away, something new flickered into existence. A single point in the sky was brightening dramatically. Immediately, this triggered the telescope's automated alert system, and news of the unknown transient spread to the astronomical community across the world. In that galaxy, a star had just died. What Atlas caught was a Type 2 supernova. Right as it happened, this was what's known as a Type 2 plateau supernova, or Type 2P. This is the textbook death of a massive star, specifically a red super giant. For most of their lives, stars exist in a delicate balance. The immense force of gravity trying to crush them inward is perfectly counteracted by the outward pressure from nuclear fusion in their core. Stars spend their lives fusing lighter elements into heavier ones, working their way up the periodic table until finally they create iron. But this is where the chain stops. It's a dead end. With no more energy releasing fusion available, the star has run out of fuel. The outward pressure disappears. Without that support, the core collapses on itself at breakneck speeds. The outer layers of the star come crashing down onto this newly hyperdense core and then rebound in a cataclysmic explosion. The shock wave from this rebound then has to travel from a star's core all the way to its surface. The moment it breaks through is called the shock breakout, and it unleashes a brilliant but incredibly brief flash of light. This shock breakout phase is the holy grail for supernova researchers. It's the purest signal from the explosion before the ejected material has had time to slam into any surrounding gas and dust. The problem is this phase is fleeting, lasting only hours. To catch it, you have to be looking at the right place at exactly the right time. For decades, it remained a theoretical event. But with SN 2024 GGI, everything changed. The story of how we captured this event is almost as incredible as the discovery itself. The notification for SN 2024 GGI went out to astronomers worldwide. At that exact moment, Yang, an assistant professor at Tsinghua University and the lead author of the resulting study, had just landed in San Francisco after a long flight. Imagine stepping off a plane, turning on your phone, and seeing an alert that could define your career. He and his colleagues knew what this meant. This was their chance to see for the first time the true shape of a supernova explosion in real time. But they had no time to waste. the pristine fingerprint of the core collapse, the very thing needed to understand how massive stars die will be gone forever. So while most of the world slept, Yang and his team worked through the night, drafting an emergency proposal to the European Southern Observatory. They urgently needed time on one of the most powerful instruments on Earth, the Very Large Telescope, or VLT in Chile. Luckily, YESO immediately approved their request. At the Paranal Observatory in the high dry air of the Atacama Desert, the VLT swung towards galaxy NGC 3621. Just 26 hours after the supernova was first detected, its formidable eye was focused on the fading flash. By the slimmest of margins, they'd pulled it off, but simply taking a picture wouldn't be enough. They weren't just try to see the supernova. They were after a very specific signature hidden in its light. Mounted on the VLT is an instrument called FIRS-2, which measures something called spectral polarimetry. Normally, light waves vibrate in all directions. This is unpolarized light. But polarized light has waves that only vibrate in one direction. For example, when sunlight reflects off a flat surface like water, it becomes partially polarized. It's also why when you put on polarized sunglasses, this glare disappears. They're designed to filter out that kind of polarized light. In the context of supernova, Yang was interested in polarized light because of what it could reveal about the shape of the explosion. A perfectly spherical explosion scatters light equally in all directions, producing no polarization at all. But an asymmetric explosion, one that is symmetrical along one axis like a football, would polarize light in a specific pattern. By carefully measuring how the light from SN 2024 GGI is polarized, we could deduce the shape of its explosion. From there, we can start to figure out the mechanism that caused it. For over 50 years, scientists have tried to explain the physical processes that trigger a supernova explosion. From the creative rubble emerged two leading ideas. The first says that neutrinos must have something to do with it. After the core collapses, a tiny fraction of the neutrinos it releases deposit their energy into the material above the core, heating it from below. This creates a violent convection. State-of-the-art 3D simulations show these explosions would be highly irregular and asymmetric. The second theory says jets are behind the boom instead. The collapsing core forms a rapidly rotating neutron star. Magnetic fields get wound up and amplified by the rotation, channeling material into two powerful jets shooting out along the star's rotation axis. In this scenario, the blast would produce axial symmetry, leading to a football-shaped or olive-shaped geometry. So what do you think, Yangs? VLT observation showed for SN 2024. Pause the video and comment below. An explosion emoji if you think it's highly irregular and asymmetric like the neutrino-driven model predicts. Or an American football emoji if you think it's symmetrical along an axis like the jet model predicts. So, moment of truth. This is what SN 2024 GGI looked like. The spectral polarimetry data revealed a clear, well-defined axis of symmetry and an olive or football-shaped explosion. At first, it seemed like a clear win for the jet-driven theory. Finally, we had the conclusive observational data we'd always been missing. Case closed, right? If only it were that simple. These models are based on simulations and theory. The neutrino models have shortcomings, often producing explosions in order of magnitude weaker than what we observe. But the jet-driven theories aren't flawless either. When astrophysicists simulate them in 3D, the jets can become unstable, twisting and kinking instead of punching cleanly through the star. The explosion never happens. Yet, SN 2024. GGI clearly exploded. So there must be something else going on. The solution might lie in flipping the old theory on its head. What if the fatal wobbling and kinking of the jets is actually an essential part of the explosion? If jets rapidly jitter, they're forced to deposit their energy close to the core, creating pressurized bubbles that merge and drive the explosion. The jets themselves are chaotic, but the overall explosion geometry remains axially symmetric, just like SN 2024 GGI. So, where does this leave us? Well, SN 2024 GGI definitely showed us that explosions can have an organized axial symmetry. How it arises remains a mystery. It also raises questions about other supernovae, like Cassiopeia, which don't follow this axial symmetry. Are they caused by neutrinos? Which factors determine what kind of explosion occurs? This might come as a shock, but we can't know without more data. The good news is, thanks to the supernova's relative closeness, astronomers look back at old Hubble images and found the star that died. It was a red supergiant, about 12 to 15 times the mass of our Sun. This makes SN 2024 GGI a textbook example, a benchmark against which we can now test all our theories. And this benchmark is telling us our standard theories were incomplete. This discovery plugs a huge gap in our observational timeline of a star's death. We have plenty of data on stars before they explode and mountains of data on their remnants. But that first day, that fleeting period of the shock breakout, was largely a black box. SN 2024 GGI has illuminated that box. Understanding how these stars explode is fundamental. These events create and distribute most of the heavy elements in the universe. The oxygen we breathe, the calcium in our bones, and the iron in our blood were all forged in the heart of a massive star and flung across space. This non-spherical explosion suggests that this mixing process may be more directional than we thought. And that's exactly what researchers plan to do as more automated survey systems like Atlas come online worldwide. Our ability to catch transient events in their earliest moments will only improve. Astronomers are optimistic that they'll be able to regularly catch supernovae within 24 hours of their explosion from a single, rapidly brightening point of light. 22 million light years away. A new chapter in astronomy has been written. For the very first time, we have seen the true shape of a supernova at the moment of its birth. Not a perfect sphere, but a distinct olive-shaped blast. This one, fact, is forcing a fundamental rethink of how massive stars end their lives. It points away from chaotic boiling models and toward a more orderly, powerful engine, likely driven by the star's own rotation. We now know that at least some, and perhaps many, supernovae are born lopsided. This discovery provides a critical anchor point for all future simulations. It's a powerful reminder that the universe is always more complex, more elegant, and more surprising than we can imagine. As we build more powerful surveys and more agile telescopes, catching stars in the act of exploding may become not a once-in-a-lifetime event, but a new tool to probe the deepest mysteries of the cosmos. The universe just showed us one of its most private moments, and it was not all what we expected. I'd love to hear what you think about this, so drop a comment below. If you enjoyed our conversation today, please share this video and subscribe to help the channel grow. Every bit of support counts.